Welcome, ladies and gentlemen. We've seen how we can differentiate an implicit relation going term by term with just application of the chain rule. That is, anytime we differentiate a y term with respect to x, it's going to spit out a times the derivative of the base, a y prime, right, in accordance with the chain rule. And so we're all ready to go with our generation of a tangent line, right, so long as I have the same three things. I need the x coordinate of the point of tangency, the y coordinate of the point of tangency, and the slope of the tangent line. It looks like, by golly, we've gotten two of these things for free already in my setup. We want to write an equation of the tangent line to the curve at the point -8, 6. So we have our x coordinate of the point of tangency, our y coordinate of the point of tangency. We just need our slope of the tangent line. And where, pray tell me, can we go to find my slope of the tangent line? Paul?
Well, I started doing the derivative of both sides.
But yeah, absolutely, because to get the slope of the tangent line, we need what expression?
The explicit. Oh, you need the y prime. You need with the y prime.
Absolutely. We need to know what y prime is so we can get the slope of my curve at any point along it. So let's go ahead and generate y prime. So yes, I agree, Paul. Let's go term by term and differentiate both sides with respect to x. Here we go. The derivative with respect to x of x squared is 2x plus, now let's do the derivative with respect to x of y squared, squiggle underline in blue. So we'll use the power rule. The derivative of a power function is exponent times the base raised to 1 less, and then times the derivative of the base. What's the derivative of y? Y prime. So we just do our power rule with the chain because y is itself a function of x. Awesome. And then equals the derivative of 100 with respect to x is 0. So right here, if you had your first line, your differentiation correct. Awesome. Now we needed y prime in order to find the slope of the tangent line, so we'll isolate y prime by adding and subtracting, multiplying, or dividing. So our y prime expression after solving for y prime, I get opposite of x over y. Raise your hand if you got the same thing. Opposite of x over y. Woohoo! This will give me the slope of that relation anywhere along it based on what x comma y coordinate I'm talking about. What x comma y coordinate are we talking about? We're talking about the point -8, 6. And so to get my slope of the tangent line, we'll evaluate this when x equals -8 and y equals 6. And so we'll evaluate my equator tangency to generate the slope of the tangent line. It looks like I'm getting a positive 8/6 equals 4/3. So I'm getting 4/3. Raise your hand if you have 4/3 for your slope of the tangent line. And that completes our 3 pieces of the puzzle. So we're writing the equation of a line tangent to a curve at the point -8, 6 with slope 4/3. Point slope form is my go-to form for that. So y minus a -8. I'm sorry, y minus 6 equals 4/3 times quantity. X minus a -8 is x plus 8. And I can solve that for y. If I wanted to verify graphically, I'll have to enter my grapher so I can solve that for y. If the directions didn't specify, I could stop right there. That is an equation of the line tangent to the curve, but it's probably going to be useful for us to check graphically if I were to solve this for y. So let's go ahead and do that. I'll get y equals 4/3 x. And if we were to solve that for y, it looks like we could multiply across and get 32/3. Right, 32/3 plus 6 would be plus 18/3. So what is that? 50/3? 50/3? And that's plus. Okay. So we've gone ahead and rewritten this solve for y so we can check our tangent line graphically. So everybody to the graphers. Here we go. In our graphers, we're going to go ahead and enter our original y equals. It's not y equals. How are we going to enter that in my original? No problem. I know that I can solve that for y by subtracting over the x squared and then taking the positive and negative square root. Remember, this is a relation, right? And not all relations are functions. This is what curve when graphed in the xy coordinate plane. What function family? Sorry, can't say function family. What relation family? Almost. My coefficients on the squared terms are both 1, so it's a circle, right? A circle. I guess you could say that's a special kind of ellipse where the major and minor axes, right, are equivalent lengths. So that's a circle. Bam! So let's solve. Ready? Go. Y equals the plus n minus square root of 100 minus x squared. And if I want the, oh, lag. Take one step, drag the emulator. Take one step, drag the emulator. And I also want the bottom half of that semicircle, so I'll also do opposite of y1, bars, y bars, function y1. So that's going to be my top half, my top arc, my bottom arc. And I want to get a good picture of this, so I'm going to adjust my window to negative 15 to positive 15. And negative 15 to positive 15. And I'm going to zoom square so that I can get a circle. You guys, you can adjust for the fact that your viewing window is a rectangle by doing zoom square. So I'm going to do zoom 5 to do z squared, and that'll correct for that rectangular window and make this look more like a circle. So here we go. Z5, zoom square. Isn't that sweet? So you can see how that counteracts the rectangular viewing window. Otherwise, it looks like an ellipse anyhow. All right, we want to know the equation of the line tangent to the curve at negative 8, 6. So let's enter our equation line first. Let's enter that, what we got, 4. Let's enter 4 thirds x plus 50 thirds. What happened? Went too fast? Went not fast enough? Okay, moment of truth. So if we're right, then that should touch the point negative 8 comma 6, and I can verify by doing trace. Negative 8. Enter. And it looks to me like the cursor has jumped on the point of tangency. And so it looks like, hey, we did a pretty good job. What other way could we verify using our grapher, right? What other way could we verify using our grapher? Sophia? The draw. We could utilize the draw tangent feature. Everybody, let's try that. So on my graphing calculator, I could do, I'm going to put this, I better grab this though before I forget. On my graphing calculator, I could utilize the draw feature by doing from the graph, second program, right, is the draw menu, and the fifth option is tangent. I'm going to take a screenshot of that too. And I'm going to enter the x value concern. I want negative 8 on that top function. Enter. And it's overwritten my equation of the tangent line. It's now got the blue line still on there, and it spits out an equation of the line. What? Y equals 1.333333x? Oh, y equals 4 thirds x plus 16.6666667? Well, that would be 16 and 2 thirds, right? 16 and 2 thirds, 48 and 2 thirds. I mean, sorry, 48, 16 goes in 48, right? 1, 2, 3, 16 times 3 and 2 thirds. Yes, so we get it. Fractions are hard. Decimals are hard. I mean, they taste good, right? I like fractions. I like decimals. Very small rocks. All right. What questions do you guys have about your graphical verification? No? Awesome. I'm super excited about today. Let's go ahead and verify this a different way, and so we can compare our ways. So we need to do this explicitly now, right? Let's go ahead and do this algebraically explicitly. In this case, we'd have to solve for y first before performing our differentiation, and we can compare that with our implicit differentiation in the first part. So let's solve for y first. I know that y equals the positive and negative square root of 100 minus x squared. If I'm generating the equation of the line tangent to the curve at negative 8 comma 6, which arc of the semicircle will I use? The positive square root or the negative square root? The positive. So we'll differentiate the top half in order to get y prime. All right, let's do it. So I saw many of you got to here, and then we kind of started our discussion. So let's see, y prime can be explicitly generated by utilizing what rule? Well, we're going to go ahead and use the power rule. We're going to differentiate that quantity to the 1/2 power. And so before I differentiate, it might be useful to rewrite this as y equals quantity 100 minus x squared all to the 1/2 power. Then my differentiation, we'll utilize the power rule, and I'll get exponent times the base raised to the 1 less. What's 1 less than 1/2? Negative 1/2. Times the derivative of the base. Several people forgot that on your rules quiz last class, right? Exponent times the base raised to 1 less times the derivative of the base, right? My chain rule is built in all of our verbal words so that we don't forget important things like times the derivative of the base, which in this case is negative 2x. We can now rewrite as y prime equals, and we'll go ahead and simplify. I'm getting negative x over root 100 minus x squared. What happened to my 2's? Well, negative 2 times the 1/2 is just negative 1. My x is on top, and a negative exponent, right, is the same as a positive exponent on the bottom. 1/2 exponent is the same as a square root. How do we do with our y prime? So who got all the way to y prime explicitly? Yes? Okay. I'm sorry, but I can't help asking which differentiation was easier, implicit or explicit? Implicit was much easier to handle. There's a chain rule here, too much floating around, and so it was much easier to handle my implicit differentiation, and that's its real power. Okay, but we can still finish it in a different way. I'm now going to evaluate this at the point when x equals negative 8, so we'll go ahead and get opposite of negative 8 over square root of 100 minus negative 8 squared is 64, so 100 minus 64, and that is 8 over 100 minus 64 is 36, so square root of 36. So I'm getting 8 over square root of 36 is 8/6, and 8/6 is 4/3. We win. I was worried there for a minute. So we still get 4/3. Just kidding. Not really worried. And we can then do our y minus y sub 1 in the same way. Equals quantity x minus x sub 1. So we'll just stop there. Y minus 6 equals 4/3 times quantity x minus negative 8 is x plus 8. And in this case, we do the dot, dot, dot. Dot, dot, dot. That's fun. That's my favorite part. You know the rest. You know the deal. What questions do you have about today's Bellwork? Okay. Then let's give you some credit for those you complete on OTL number 6, please, at this time. Make sure that your name, 2A, and number 6 are clearly labeled. If you have multiple pages, please staple those together. There's a stapler on the side activity table, as well as on the front table. Out of 24, divide, enter. Multiply by 2, and let's box the infinite campus score around to the nearest half point, 0 to 2. Thank you, front rowers, for making sure they're facing the same direction. I appreciate your help. Very good? Awesome. I'm super excited about our discussion today. Today we're going to introduce a concept that always shows up as a real-life application on the AP exam. And so it may show up on the multiple choice portion of the AP exam. It may show up as a free response question. Several of the last years on the free response portion, a question has involved related rates for at least one of its parts. And so we don't know what this year's exam is going to look like, but I bet that related rates is going to show up, right, and at least the multiple choice portion, if not the free response as well, okay? And so we're going to generate that concept today in our introduction to related rates, and we have an activity for that. We originally generated data using the CBL units that attach to the TI calculator and a motion detector, and generated data, but in the interest of time, it ended up being a long process that took several days. And so in the interest of time, we're going to use Michaela Breinig and Jackie Vandenbroek's data that was generated several years ago. So we're going to go ahead and just use their data. I've gone ahead and copied that into a data table, and we're going to use that data so that everybody is now generating kind of the same result. So we're going to use that calculated data from several years ago in our activity today as a means for saving time. In our related rates activity, you can earn stamps on number 5, number 7, and number summary number 3. Okay, we're going to come back together for number 4 on the summary after everybody's gotten their number 3 stamp and our closer at the end. So make sure you circle your stamped eligible items, number 5, 7, summary number 3. I'm halfway through your rules quiz, but I'm still continuing to grade those, and so next class period you should be getting your rules quiz back. And my goal is to include those on our quarter progress check. And so I know that the quarter post is not a GPA affecting. Now we have semesterized grading. However, I wanted to include the rules quiz in the quarter post. That's coming up next week, and so I'll continue to grade those. The next class we should get those back so you can see exactly how you did. And once again, I'll put that in before I finalize grades for the quarter post. Question about what the next segment of this class is going to look like? Then we'll need at least 5 minutes at the end, so we're aiming to come back together around 11:25, and that should be good for our closure, okay? Awesome. Thanks, ladies and gentlemen. I'll pause the recording and you can get scooted into your cooperative learning groups, and I'll be around momentarily. Thank you, ladies and gentlemen, for returning to the desks. Let's go ahead and take a look at now our summary number 4. And so you guys saw in number 3 that really X and Y, the distance of the base of the ladder back to the barn, and the distance Y, the height of the top of the ladder above ground, both depend on time. That is, as time goes on, as time increases, both X and Y are changing. And so a related rates problem exists when 2 or more related variables are each changing with respect to time, okay? So if we start out with our Pythagorean theorem, that was the horizontal distance from the base of the ladder back to the barn, X. And Y is the vertical distance, right, of the top of the ladder down to the ground. Those quantities, X, Y, and the meter stick, form a right triangle. So we can represent this equation, X squared plus Y squared equals 130 squared. And now we're going to differentiate both sides with respect to time in order to get our rates of change involved. And so for number 4 in your packet, we could differentiate both sides with respect to time, just like we differentiated both sides with respect to X of an implicit differentiation back for Bellwork to generate Y prime. When we do so, right, we spit out well, not an X prime or a Y prime this time, but a dx dt or a dy dt, so that we're explicitly saying, right, using our Leibniz notation, the rate of change in what with respect to time? The rate of change in what with respect to time? Let's go ahead and try that together. And so if I differentiate term by term with respect to time, I'll be using the chain rule. That is to say, the derivative of x squared with respect to time, we'll start out with your power rule. Here we go. The derivative of x squared is exponent times the base, raised to 1 less, and then times the derivative of the base. What's the derivative of my base x with respect to time? There's my dx dt. So we're going to use Leibniz notation for related rates because it explicitly shows what variable is changing with respect to what. Plus, and now let's go ahead and differentiate our y term with respect to time. So the derivative of y squared with respect to time, I'll still use the power rule, right? But it's the chain rule, where my base isn't just t, my base is y. So every time I differentiate that y term, it'll spit out a times the derivative of the base. Let's try that. So the derivative of y squared with respect to time is exponent times the base raised to 1 less times the derivative of the base. What's the derivative of y with respect to time? dy dt. Awesome. And then on the right-hand side, the derivative with respect to time of 100 squared is 0 because the derivative of anything is 0. Nice job. That's it. Now, depending upon what it is we're asked about, and we'll do this next class, right? We'll be solving real-life problems that involve related rates questions from your AP Calculus exam. We'll isolate one of these rates. If we wanted to know how quickly the wall was sliding down, right? The ladder was sliding down the wall at a given time, we would solve for dy dt, because that represents the instantaneous rate of change in the height of the ladder above the ground. If we want to know how quickly the base was sliding away from the wall at a given time, then we would solve for dx dt, because that represents the instantaneous rate of change, right, in the distance of the base of the ladder away from the wall, and so on and so forth. So at this stage in our life, we need to recognize that a related rates problem exists when one or more variables then is changing with respect to time. So they're changing with respect to time. We differentiate all terms with respect to time, and each time we differentiate an x term or a y term or a theta term, it's going to spit out a d theta dt or a dx dt or a dy dt in accordance with the chain rule. All right, so now we need to go back to our note sheet. On a regular note sheet today, let's go ahead and fill in our blank for closure. Then we'll be done and you'll have a chance to work on it, continue working on your 4-9 related rates problems to set up for next class. So, a related rates problem exists when two or more quantities are changing with respect to blank. Don't say it out loud, just fill it in. Then we'll suppose a circular ripple pattern in a pool is growing larger. So if we were to drop a stone in a pool, we know that circular ripples emanate from the site of the splash and grow outwards. Let's find an expression that gives dAdt, that is the rate of change in the area with respect to time, for those circular ripples, A equals pi r squared, or I should say the area enclosed by a circular ripple. Okay, so a related rates problem exists when two or more quantities are changing with respect to blank. Savannah?
Time.
Time, right? That's our related rates. Let's suppose a circular ripple then in a pool is growing larger. Find an expression for dAdt. All right, so let's start with our original equation. In the latter problem with Jackie and Michaela's data, we started with x squared plus y squared equals 100 squared. Here, we're starting with a equals pi r squared. So we'll start with our original relation, a equals pi r squared. And we will differentiate both sides with respect to time, right? These quantities are changing with respect to time. As the circular ripple grows, right, the radius of my circle is changing with respect to time. The area enclosed by the circular ripple is changing with respect to time. Time is the independent variable, and both these quantities are changing. Let's go ahead and differentiate both sides with respect to time. So ddt, the derivative with respect to time, we'll take the derivative of both sides. What's the derivative with respect to time of A? dAdt, right? It's 1 dAdt, yes. The derivative with respect to time of area is dAdt. That's our Leibniz notation, so we explicitly see what's changing with respect to what. So we won't use primes when we're using related rates problems. The way we use prime notation, curves that represent our slope of the tangent. Equals, and now let's differentiate pi r squared with respect to time. What rule will we use? Well, a couple. We use constant multiple and power rule, right? So we'll differentiate this right-hand side. Here we go. Exponent times the base raised to 1 less. I've got a constant multiplier of pi there, so this would be 2 pi r to the first, and then times the derivative of the base. The base in this power is r. What's the derivative of r with respect to time? dr dt. So basically we do our same rules as before, it's just every time we differentiate a variable with respect to time, it spits out a dr dt, a dA dt, a dx dt, a d theta dt. Awesome. So in this case, dA dt is given by 2 pi r dr dt. Now we can determine, if given some information, how quickly the area is increasing, right, at a radius of, right, 30 centimeters or whatever. So when we're given information, we can now solve it. All right, part of your OTL includes that 4-9 related rates problem, the instant in time. It's vital that you complete that to make sure that you are set up to understand our related rates main day of notes next class. And so this was our introduction day. Next class is going to be our main topic and discussion of related rates, which is it's always an application problem on the real AP exam. So it's important we get a firm foundation for this. Next week we'll do implicit differentiation for our Moodle discussion forum, but the following week will be a related rates post. So we'll get a chance to practice this. awesome work today. I'm gonna go ahead and stop the recording.